back voltage or back EMF. Recall how an electric motor works. Let me zoom in. We're going to be doing the right-hand rule twice. Now, let's imagine, because this is a three-dimensional diagram, let's imagine we're looking down at this from the top. So when I say down, that's going to be into the page. When I say up, that's out of the page. When I say towards me, that's like along the paper towards me. Okay? What's happening here? Well, we said the way an electric motor works is we supply current. We send current going this way. So all of you right now, point your thumbs, your right thumbs, in the direction of the current. If you want to, we can use my screen. Let's use my screen. So all of us would kind of point our thumbs straight up. What direction is the magnetic field? Magnetic field lines always point from what to what? North to south. So I've got to kind of bend. I think my right hand would point that way. On the left side, right where this arrow is, what direction will the armature experience a force? Down, or I'm going to say into the page. So what you can do is draw a little arrow pointing right there and say F equals, what's our symbol for into the page? Arrow feathers going away from us. Is that okay, Anthony? Yeah? Okay. Oh, and on the right-hand side of this armature, Jeff, the current is coming towards us. So if I point my thumb toward or downwards and slide over, you know what? I think on the right-hand side, coming towards us, what that's going to do is it's going to cause this motor to spin. That's not new. That we actually looked at a few days ago, how an electric motor works. But now we're going to take it one step further. You okay with that, Cole? Okay. As soon as it starts to spin, now, Cole, I want to focus on one little proton right by the arrow right there. As soon as it starts to spin, not only is this proton moving up and away from us, as soon as it starts to spin, it's also moving into the page. Into the page. Because it's locked inside that armature. So if you point your thumbs down into the page, magnetic field that way, which way will that proton experience a force as soon as it starts to spin? I think as soon as it starts to spin, it's going to be back against the battery, isn't it? Does that make sense, Kai? Now, that doesn't happen when it's standing still. But it turns out now, as soon as it starts to spin, now not only do you have it moving because of the current, it's moving in a 90-degree direction because of the spinning wheel. And if you use your right-hand rule, you're getting a back voltage. That's what we call it, a back EMF. Oh, and the same thing is happening on the right-hand side. If I look at a proton right here, now it's moving up this way. If I point my thumb up, oh, didn't want to erase that one. If I point my thumb up, magnetic field that way, it's now going to feel, so boom, thumb up the page, magnetic field, my palm is now pointing into the page. It's going to feel, sorry, let me try that again. Pointing it the wrong way. It's moving straight up, which is coming out of the page towards me. Magnetic field that way. It's also going to get pushed along the wire. Change colors, Mr. Dueck. You're using blue. It's also going to feel a force from the spin, and that's also against, instead of calling it the battery, can I call it source voltage? That's better. What that means is, as I said at the beginning of this lesson, any motor bin is automatically a generator, but it's a generator in the non-helpful direction. You see, if coal, it actually created a voltage in the same direction as this battery, that means as soon as the motor started running, instead of 6 volts, we'd have 7 volts, and now it would spin faster. And instead of 7 volts, now we'd have 8 volts, and now it would spin faster. Instead of 8 volts, now we'd have 9 volts, and we'd have perpetual motion. Instead, what happens, let's suppose that my source is a 6-volt battery. When this starts to spin, maybe it generates 1 volt in the opposite direction. So instead of a net voltage of 6 volts, if you have 6 volts this way and 1 volt this way, what's your net voltage? 5 volts. And as it spins faster and faster and faster, what do you think happens to this back voltage? Bigger, smaller, or stays the same? Bigger, because it really comes out of this. Oh. As your speed increases, your back EMF increases. Don't write that down, Darian. It's a bad analogy. Sorry, I should have said don't write that down. Okay? So what I wrote here is, notice, once the motor begins to spin, what happens? A back EMF or back voltage is created since the spin forces charges back against the source current. And that comes from the, what does RHR stand for? Right-hand rule. But it's the right-hand rule done twice. The right-hand rule, first of all, explains why it starts to move, but then the right-hand rule explains as soon as it starts to move, now you've got a second right-hand rule coming back at you. Is that okay, Jeff? We call this the back voltage, or a back EMF. This also explains what the maximum speed of any electric motor is. You know what the maximum speed of any electric motor is? It's when the back EMF equals the source EMF. In other words, if you hook this motor up to a 6-volt battery and it spins faster and faster and faster and faster, it'll stop speeding up when the back EMF equals 6 volts. Because if you have 6 volts this way and 6 volts this way, what's your net voltage? There's nothing left to speed it up. You want it to go faster? Hook up a bigger battery. Go to a 12-volt battery. Now it will spin faster. But it won't spin faster just because you want it. You got to go to a bigger battery. Now your limiting speed will be whatever creates a back EMF of 12 volts. That's your maximum speed. Okay. Let's fill in some key concepts. Back EMF is created by the spinning armature, and you can put in brackets RHR, right-hand rule. Remember, the armature is the fancy name for the coil of wires in a motor. The amount of back EMF is proportional to the speed of the motor. If it spins faster, you get a bigger back EMF. Now, listen close. If it spins faster, you get a bigger back EMF, you get a smaller net voltage. Okay. Your overall net voltage gets smaller. Part C is supposed to be intuitively obvious. When the motor starts out at rest, the back EMF equals 0. You need to know that, though. That's going to actually come in very handy, it turns out. When the motor is at its maximum operating speed, the back EMF equals the source voltage. i.e., the net voltage equals 0. Compare back EMF to the supply voltage. Well, first of all, it can never be bigger than the supply voltage because that would be getting free voltage, free energy, because voltage is energy per coulomb. Turns out it's going to look like this. Your source EMF, and I'll use the EMF symbol for that, otherwise I get V's everywhere in this equation, minus your back EMF equals your net voltage, whatever's left over. But V equals what times what? Ohm's law. V equals what times what? Okay, so instead of writing net voltage, I'm going to write I times little r. Now let me explain what this is. This is the current that's left over in the armature, the spinning motor, the spinning rotor, and this is the resistance of the armature. And I used a lowercase r because ideally we want our motor to have small resistance. If it had a big resistance, that would be like a stove, and the motor would heat up and get hot very quickly. We don't want our motor to get hot and heat up really quickly. So to symbolize that, we'll use a lowercase r to say, just like the difference between big M and little m in the gravitational unit. Little m was small mass, little r, small resistor. Okay? But here's what we're really saying then. We're saying take your source, let's say 6 volts, minus your back voltage, let's say 5 volts. What's the net voltage? There's 1 volt left. That's what's causing the armature to speed up. That's your net voltage. Okay? Oh, and if there's no net voltage, if this is 0, your source voltage equals your back voltage, it won't speed up anymore because there's nothing left over in the armature. There's no current in the armature because remember, don't write this down, but we said the force that was causing this to spin was Bill. If there's no net voltage, then there's no net current. There's no force to spin it. It'll spin, but it won't speed up. It'll be at a constant speed, max speed. Is that okay, Anthony? Okay. Except this isn't quite how they write it on your formula sheet. On your formula sheet, they're going to plus this to this side and minus this. They're going to get the V back by itself. Here's what appears on your formula sheet. Back EMF, or back voltage, is equal to source voltage minus whatever's left over in the armature. But it really comes out of Kirchhoff's laws. From what we know of if you have 2 batteries that are opposing each other. The mathematical, turn the page, analysis of a motor is quite straightforward. The equivalent for a circuit for a motor includes the resistance R of the motor coil wires and the back EMF. You know what? Here's what it really looks like. You have your supply voltage, the current is going this way. And it causes this motor over here to spin. As soon as it starts to spin, there's going to be a back EMF going this way. So what we have then is this. The net voltage is your source minus the back voltage. Except instead of net voltage, I'm going to write I times R. Okay? As the motor speeds up, what happens to the back voltage? Gets bigger, smaller, or stays the same? As the motor speeds up, what happens to the back EMF, the back voltage? Gets bigger, smaller, or stays the same? Jeff, what happens to your net voltage? This answer, bigger, smaller, or stays? Because the EMF is constant. So, you know what happens? R doesn't change because that's what changes is your net current gets smaller and smaller and smaller. And this is also hugely useful. Here's what this means. What heats up an electric device is the current. Because remember I said current was the number of protons going through. And when the protons go through a wire, just like when you rub your hands together, you do generate electric friction. What heats up a wire is current. Jeff, you ready? I'm going to pick on you again. As we speed up, what happens to the back voltage? It gets bigger. What happens to my net voltage? What happens to my net current? It gets smaller. You know what that means? What that means is electric motors are at their coolest when they're at their fastest, which is very different from a gas motor. When you floor a gasoline engine, the hotter it gets, does it become more efficient when it runs faster? No! But an electric motor does. In other words, an electric car is happiest when you're flooring it. That's why I think electric cars are part of the future. Now you're saying, wait a minute, that doesn't sound very safe. No. you can control the maximum speed by the size of the battery you put in there. So, but once you have that maximum speed controlled, an electric car is happiest at its maximum speed. It's the most efficient. Or let me put it another way. If you've ever used power tools, like a power drill, and you're trying to use it to undo a really, really, really stubborn screw, and so you're giving it the trigger, but the drill is prevented from turning, you're going to feel the motor heat up an awful lot. Why? If it's not turning, what's the back voltage? If it's not turning, what's the... Huh? You're right, Miller? Zero. So that means your current is now at its maximum, because R doesn't change. This had to get bigger because... Oh, sorry. If it's not turning, what's the back voltage? Zero. What's the net voltage? At its maximum, because the net voltage is the EMF. Your thing is going to get really, really hot. Now, those of you that have used power tools, you may have learned this. How do you cool it off? You remove it off of load, and you floor it. Off no load. And it'll cool off really quickly. Why? Because you've just created a much larger back voltage, a much smaller net voltage, a much smaller current, cooler appliance. It's a nice thing, Roddy, about electric motors. Unlike almost any other motor out there, they're at their most efficient when they're at their highest revs. Ah! Very handy. Very handy. Oh, so here's our equivalent circuit. But again, this is exactly the same equation as I had right here, except I got the V back by itself. It says apply Kirchhoff's voltage law to the motor circuit. Didn't we? Right? Because this is an opposing voltage, it's going to be net voltage minus opposing voltage, net voltage, source voltage minus opposing voltage gives you whatever's left, and it's got to be left somewhere. Oh, the only other resistor is the armature. I times R. Is that all right? So in the box, we can say this. And I'll put wings to make sure that we know that's voltage and not velocity. The back voltage is equal to your source EMF or your supply voltage, and I'll draw a little arrow from the V supply. I'm using the EMF symbol because otherwise I have two V's in my equation. That gets really confusing. Minus, don't write this next bit down, it's minus the voltage left in the armature. Oh, you know what? Minus I times little r, which is a much shorter way of writing the voltage left over in the armature. Yeah? Okay. Key ideas, Anthony. You need to know that the back EMF is 0 when you're at rest. And I'll show you why in a little bit, why that's so handy. It's at its maximum at the maximum speed. Now, I should be, in real life, in our magic physics world, the top speed, Kylie, is when your source equals your back. But in real life, the armature does have always some voltage left in it because there is always some net current, because there's resistance in the wires and things as well. So in real life, when you do rev an electric motor at full, you will feel some heat. But it's certainly the most efficient. You're not going to feel it overheating. You're going to overheat a motor under load when you give it current and you don't let it turn. That's when you're going to burn out a motor. I keep forgetting to do this, and I forgot again this year. Really, example 3 should come after example 4. Ben, I am going to say I like example 3, I like example 3, I like example 3. Absolutely, but let's do example 4 first, because example 4 is much more plug and chug. Josh! What are they asking me to find in example 4? Oh, you know what? The back EMF, and this formula is on your formula sheet, is equal to source minus I times R. Josh, did they give me the source EMF? What? 120. Minus. Did they give me the current running through this motor at this particular speed? Did they give me the resistance of the motor or the armature of the motor, which is really the only resistor? What's the back EMF right now? 6 times 12 is 72. 120 take away 72. Double check me. I think it's 48. What that also means, there's 48 volts left over that can cause this motor to go faster. There's still, you can get this motor to go faster if you need to. That's 2 plug and chug. Josh, that's too easy. Let's go back to example 3. A motor is connected to a 100-volt supply. Initially, with the motor at rest, the current is 5 amps. You know what? This is very, very, very important. Can you underline at rest? That's the key to solving this question. You'll see in a second. When the motor is running, the back EMF is measured as 20 volts. Josh, what does part A want me to find? And it is mentioning back EMF, so I'm going to start out by going yes? What did you say they want me to find here? Let's get the R by itself. You know what? What's in front of the I times R? A negative. Remember, we did this all the time in forces with tension. Josh, I'm going to plus this to this side. At the same time, I'm going to minus that to that side. We did that all the time for forces to get rid of a negative because it was so convenient. So I'm going to write this as IR equals E minus V back. That looks familiar, Mr. Dueck. It should. Right there. Right? It's Kirchhoff's law. It's skiing. Yes, you have the equation on your formula sheet, but an argument could be made, Sarah, that you should be able to derive it from your circuitry rules. I won't. It's on your formula sheet. What do you say we're trying to find there, Josh? Let's get the R by itself. How? Did they tell me the source voltage? Okay. Did they tell me the back voltage?
When it's running, it's 20 volts.
Did they tell me the current when it's running?
5 amps.
That's the current when it's running?
Oh,
Ah! So let's try this again. Did they tell me the source voltage? 120. Did they tell me a different current?
like at rest?
Oh, they did tell me a different current. What did they tell me? The current at rest?
Yep.
Ready? Did they tell me the back EMF at rest? No, they didn't need to.
Is it 0?
That's the key to doing this question, to realize that if I know the current at rest, I know the back EMF at rest. It's 0. So we can now go like this. What was the source, Josh?
100 volts.
Minus, I'll put the 0 in so you know that's what we did. In your notes, in your homework, you don't need to. 100, not 120. Divided by, what was the current at rest?
5 amps.
Josh, I'll bet you can do that in your head.
20 ohms.
Now, that's the resistor of the armature, and that won't change for the actual that's always going to be the same. What will change is the current and the back voltage. Those depend on the speed, but not the resistance. That's the physical component of the armature. Hey, what's part B want me to find?
Current for when it's running.
Oh. Well, back voltage, back EMF equals source minus. Let's get the I by itself. Oh, what's right in front of the I?
Negative.
Hey, can I plus this to this side and minus that to that side? This is kind of familiar, Mr. Okay. We get IR, or net voltage, equals source minus back. What are we trying to find, sir?
Current.
How would I get the I by itself?
Divided by R.
Double check. Did they tell me the source voltage? Did they tell me the back voltage at speed?
Yep.
Did they tell me the... Oh, that's why I had to do part A first. Now, I like this question, I like this question, I like this question. I won't ask you part A first, though. I will just go straight to part B. I will simply give you the information, and I will say, find the operating current for when the motor is running, and you'll have to clue in, Jeff. They didn't give me the resistance, but I can figure it out because when it's standing still, they'll never tell me this. I know the back EMF is 0, and that gives me enough to find the resistance. Okay? Resistance, in this case, is not futile. Let's keep going. Source was 100. What was the back EMF at speed, Josh?
20 volts.
Divided by also 20?
Yep.
Hey, I bet you can do that in your head as well.
80
80 divided by 20, which all of us know is actually what?
1.
And I'll go to 2 sig figs, so I'll go 4.0 amps. Okay. Oh, and the fact that there's still some current left over means there's still some force on the armature, which means I can still get more speed out, more juice out of this if I need to. We did example 4 already. Example 5. When an electric drill is prevented from turning, the motor heats up. How can we cool the motor off? Sorry? Just the way I said earlier. Yeah, that's not going to be sufficient. You understand technically you could answer that on every single test question, right? Yeah. What you said, Mr. Dueck. Which I guess is right. But
use it in the air at full speed.
Can I use that expression? Floor it? Why will that work? As speed increases, back EMF increases. What does that do? Net voltage. What happens to the net voltage? So we have our source. As your back EMF gets bigger and bigger and bigger and bigger and bigger, what happens to the net voltage, which is the source minus the back? It gets decreases. What happens to the net current? And this comes down to, all the way going back here, me saying, hey, another way to think about net voltage is I times R. R is not going to change, so if net voltage gets smaller, what has to get smaller? Oh, too far. So net current decreases. Current causes heat, so heat decreases. It's a little domino effect, Miller. The fact that speed increases, back EMF increases, net voltage decreases, net current decreases. You have fewer charges going through the armature, fewer collisions of charges into each other, less electric friction, heat goes down. And it's very counterintuitive. Most people, if you tell them that when you spin an electric motor faster, it cools off, they're just not used to that because all of their experience is internal combustion engines, which, yeah, those heat up when you floor them. Example 6 is just like example 3. I'm asking you, first of all, to find the resistance, and then I'm asking you to find the current. Try this one on your own. I'll do it up here. Let's see if we get the same answer. But, Ben, I like this question, I like this question, I like this question. Except probably I won't ask part A. I might, but probably I'll go straight to part B. Take away 4.2 is 1.8, 1.8 over 1.2, that's like 18 over 12, 3 over 2. Is that right? Okay, give you a few more minutes, but I think I'm right. I did the math in my head, but they were pretty good numbers to do math with. See you live?
Somewhat.
Okay. It's been a couple of days since grad. Got to get her sleep. So, neat applications. I talked last day about the induction cooker, right? And I did show you the Kickstarter kettle. Very cool application, though. Okay, induction cooking. I think you can get a little induction stovetop, like a little. I'll call it a one burner, even though it's not a burner; it's a solenoid. I think you can get them for about $60. They're very popular in Australia because, again, you have no heat coming off of the edges. If you've ever stood over a stove, you felt heat coming off of the edges. That's got a. Oh man, you don't need that in a hot climate. So on a hot summer day, induction cooking is much nicer. And apparently they're quite popular in dorm rooms where you don't have a full, complete kitchen. I've also read they're popular in mobile homes where it's much safer than propane. And 'cause the other nice thing, by the way, is if you leave the stove on, as long as you took the pot off, there's no heat, no big deal. Noah, you're smiling and looking at something and everyone else is looking. You're not foolishly looking at your phone or anything, are you? That would be foolish. Right, Kylie? Right. Okay. Yes? So there's a neat application. What's your homework? Basically, you can do any question that doesn't have the word transformers in it, but if you want to actually see the question numbers, Mr. Dueck. Right there. From the review, you can do those questions 2, 10, 13, 17, 21, 28, 29, 31, 41, 42, 44. Can you write that down, please? Or the shorthand version is, if it doesn't have the word transformers, it's fair game. If it does have the word transformers, after Thursday, it's fair game. What I want to do now is go through the circuitry test. Let me hit pause for a second, first of all.